Okay, so this one, we have a box on an incline. Okay, now let's draw the free body diagram here and let's compare it to what the choices they give us are. Okay, so I'm going to redraw this. My heat just kicked in, so if there's like loud buzzing noises in the background, this is my apartment getting warm. Alright, so we have this box. It's on an incline. Now, there's a couple things that we should know by now. Okay. Also, it's accelerating at 2 meters per second squared. That's going to be important later on. We're going to have to keep that in mind. So it is moving. This box is moving. It is not stationary. So the first thing is that we should know by now the weight of an object, the force of gravity, pulls straight down. Okay. It pulls straight down towards the center of the earth, and I probably could draw that straighter, but hopefully you see what I'm doing here. Pulls straight down. And once again, we know that the weight is equal to mass times the acceleration due to gravity. The normal force, we should remember, points perpendicular to its surface. So if you're at an angle, or if you're on an incline, I should say, it's just going to point 90 degrees up from that surface. And then since this box is accelerating down the incline, you're going to have a kinetic friction force parallel to the surface, okay, pointing in the opposite direction of motion. So let's compare what we drew to our answer choices here. And if we do that, we can clearly see the only correct answer here is E. Alright, now this says the magnitude of the frictional force along the plane is most nearly what? Alright, well, we have to think here. The net force acting parallel to the surface on this box is equal to the mass times 2 meters per second squared, right? Because the object is accelerating. And we should remember now that net force, in whatever direction we're talking about, is equal to the mass of the object multiplied by its overall acceleration. Now, the box is not accelerating perpendicular, right, up or down compared to its surface at all. So we should know that the normal force here should be equal to the y component, or not the y component, I should say, the perpendicular component of gravity. Okay, right? We can break up this gravity force based on this 30-degree angle. We could break this up into a perpendicular component. That's crying in the background. And a parallel component. Excuse me. So Fg perpendicular should be equal to the force of gravity. And once again, we know this angle here has to be 30 degrees. Let me write that in. Because it's going to equal the angle over here. So our force of gravity perpendicular is the adjacent side of our right triangle. So it's going to equal our hypotenuse, right, our weight, times cosine of 30 degrees. Our force of gravity that's parallel, which is going to be what's opposing the friction. So the force of gravity parallel is equal to the weight times sine of 30, because this time this side here is opposite of our angle. So it's going to equal sine of 30 degrees. Okay. Now, if we're talking about our net force here, and what we're trying to find eventually is the frictional force in number 3. Now, the net force is equal to mass times acceleration. We know that the net force is also equal to the sum of the forces acting in that direction. So the sum of the forces parallel to the surface, right, which is the direction that the acceleration is occurring, would basically be the parallel component of our gravity, so Fg parallel, minus the friction force, that's opposing that motion, and that's going to be equal to the mass, which we know is 2 kilograms, times the acceleration, which we know is 2 meters per second squared. Okay? Now, if we know the mass, we also know the weight, right? So the weight is equal to the mass, 2 kilograms, times the acceleration due to gravity, which is 10 meters per second squared. So 2 times 10, our weight is 20 newtons. So we can find here the parallel component of this gravity force. That would just be the 20 newtons times sine of 30 degrees. If we do that, let me grab a calculator here. So 20 times, I'm just plugging in here, right? Force of gravity times sine of 30 degrees. 20 times, I get 10 newtons as the parallel force here. Okay? So my force of gravity parallel, when I plug in here, is 10 newtons minus the force of friction equals 4 kilogram meters per second squared, which is basically what newtons are. I'll explain that later. And now what I can do is I could rearrange this equation in order to solve for the force of friction. So I could add the force of friction to this side, subtract 4 newtons from that side, and if I do my algebra correctly, I'll find the force of friction is 6 newtons. Okay? And once again, this all hinges on me understanding that the net force is equal to the sum of the forces acting in the direction of the acceleration. Me recognizing what the mass and accelerations are from the problem, and me realizing what the forces were that were acting parallel to the surface. After that, I had to understand how to find the parallel component of that weight, which once again is just the weight, mass times the acceleration of gravity, times sine of 30 degrees. Okay, and the acceleration due to gravity, we're going to use 10 meters per second squared. Once we found that that was 20 newtons, just sine of 30 got us 10. And then when we rearrange the equation, once again, we got 6 newtons. That was the first 3 problems.